Okay, so in this last part of this our overview, I wanted to go over association measures and hypothesis testing. And these may seem like very simplistic calculations, but it's because R is already doing everything on the background. So the first thing that I wanted to do is the correlation. And often we use the Pearson correlations, the standard or default correlation, but there are others as well. And we have already talked about correlation, and the way to do it in R is we use the core.test function. So that's the function. And then we add the variables of interest. And let's use that respiratory function variable and the walking distance variable. We also have another parameter here, use, and complete.obs is to avoid null values. I don't think we have any null values or empty values in this data for these variables, but it's also important to check. And then the method equals Pearson. There are other methods as well, but let's just use the standard. And then if we run this, we actually get a set of values, and you can see they're all here: Pearson's product, moment correlation. And there's actually more values than we need to be attentive to, but they're all kind of important. So one is the p-value. When we do a correlation test, we also get a probability value of that test. And when we see this statistical notation here with E, we can kind of see that it's very, very small. So it's hard to just figure it out, but it's fairly small. And it identifies the alternative hypothesis. True correlation is not equal to 0. So the null hypothesis is assuming that these two items are not correlated, meaning the correlation is equal to 0. So it carries out a t-test that we'll talk more about in this class, and gives us the 95% confidence interval. So we can, in this case, we can assume that within 95% confidence, we can say that the correlation is between 0.3 and 0.6. That's what this means. With 95% confidence, we can see that the correlation is 0.3 to 0.6, anywhere for that. Now, the actual correlation that it gives you, the estimate is 0.469, which is moderately to strong correlation, actually. Now, as we talked about this, the correlation depends on context. In social science, this would be very relatively strong, or at least relatively strong, if not very strong. But in medical sciences, this may be considered just moderately strong. It's certainly not 0, and the p-value is very low. So we can reject the null hypothesis, and we can accept the alternative hypothesis that the true correlation is not equal to 0. The estimate was 0.46, and the confidence interval is here. And that's the Pearson correlation statistic. Now let's go over hypothesis testing. And actually, I'm going to write out here the comments in the hypothesis testing for us to understand what we're doing. So I want to look at if there is a significant difference between genders in COPD patients. Now, I'm not thinking that if you have COPD, that's going to cause you to be male or female. But we may think that whether you're male or female, that can cause you or increase your chance of having COPD. Either way, as I mentioned before, this causal effect attribution needs more careful attention. It needs theory behind, it needs other kinds of mechanisms. So more simplistically and technically, we can ask or frame our hypothesis in plain language as, is there a significant difference, a statistically significant difference between genders in COPD patients? So we set up the null hypothesis that the proportion of COPD patients is really across genders is just 50-50, 50% are male, 50% are female. And then set up an alternative hypothesis that it's higher than 50%. So why do I think it's higher? Well, because our data set already indicates it's higher. So if we remember, if we table table COPD age, we see that table COPD age, why that's kind of weird. Oh, I'm sorry, not age, gender. We see there's 65 males, 36 females. So there's already indication that it's higher, and maybe there's other theory that suggests that men are more likely to develop COPD. So we're going to carry out a hypothesis testing of whether or not there's a significant difference between genders in COPD patients with these null hypothesis and this alternative hypothesis. And one way to do that is this proportion test of proportions, which is also called the Z test. And the way to do it is we call the function prop.test, and then for the X variable, this is the number of successes. And you can see also from the textbook we're using. So what's a success? Well, success is not really a success in this case, but just because we have a binary variable, the values that are 1, the values that are kind of different or special in our case that we're assuming. So in this case, it's going to be the males. So that's 65. N is the number of trials or the sample size. Let's say sample size. And in our case, it's 101. P is the null hypothesis you're assuming. So we're just assuming the proportion is 50%, or should be 50%. Our alternative hypothesis is that it's greater. So that's the direction. We already have previous theory and indication from this data set that we're assuming that this, once again, not success, but this the male value is going to be greater. And then we determine the confidence level that we want to test at. And it's 95%. And we just run this function and we get the result of this one sample proportion test with continuity correction. But the main information is, well, the p-value is the result. So we already see that the p-value is low. It's usually the threshold that we want to pass is 0.05, and this is below 0.05, indicating that it's very unlikely that we got these results by chance. This is why we want to see the p-value low, because we want it to be unlikely that we got these by chance. So our alternative hypothesis that true p is greater than 0.5, we can reject the null and accept the alternative hypothesis, at least for now. The 95% confidence level is 0.55 to 1. So we can be 95% confident that the proportion would be 0.55 to 1. Maybe in this case, it's not that useful, but this can be useful sometimes. And the sample p estimate is 0.64, which is usually expectedly is the percent that we got. 65 divided by 101 is going to be 64. So that's the estimate for the gender, and the important one here is the p-value. The p-value is very low; it's below 0.05. So we can reject the null, and we can accept that there is a significant difference. There is a significant difference between genders in COPD patients, toward that more males are more likely to have COPD than females. I hope this is useful for now, and I'll see you next time.